whenever the topic of superhuman AI comes up, of course, I mean, a couple years ago, it just was felt to be science fiction. Maybe these days people are taking it a little bit more seriously. But still, I mean, yes, you understand AI, but like superhuman immediately causes us to think, okay, if it's superhuman, it cannot just fully learn from us. And so built into the name or the description superhuman is that there has to be some very strong form of self-improvement. And now if you do a Google search for self-improvement, you of course get these kinds of ideas. Um, and of course AI knows about self-improvement. So the distinction to draw here is of course about the difference between knowing about the behavior versus actually acquiring the behavior and carrying it out, which are two very different things, as we all know. And in the mathematical setting, uh, and maybe as of the past year or so, this is even known that it can be done. So solve the international, do well on the International Math Olympiad, like get the gold medal. And indeed, in 2025, it won it performed at the level of a gold medalist. Uh, but of course, knowing about the behavior, it knew all along, right? It knew about IMO. So here's the outline. So I'll walk you through briefly about this history of the idea of mechanizing math, which this relates to, and then we'll talk about deep learning and AI. And the important thing for what we're talking about today is reinforcement learning, I think, and then self-improvement, and also, I mean, in general, and also in context of math. And there's a simple example of self-improvement that I was involved in, just the Girl Prover project, which I'll talk about very briefly, just a couple of slides. And then the fifth point is maybe a longer point, which I think will illustrate how superhuman behavior could come about, maybe just a taste, and then potential hurdles. Okay, so the dream of mechanized math animated a lot of mathematics in the 20th century, starting with the questions of Hilbert, where he pointed out, who was a leading mathematician of his day, and he pointed out that mathematics is formal, and he called it a game of formulae. And so it's very mechanized, right? And that led to the notion of computing soon after. And it was immediately tied to mathematics, because of those kinds of musings. And for example, deciding whether a proof exists for a given mathematical statement is uncomputable. And then a few decades later was the more real life version of difficulty. It was considered, so NP completeness. And it was discovered that this something that when this wasn't considered in the discussion of uncomputability, and now you're talking about computational complexity. And there it was shown that even if a proof of length exists, finding it may take very long time, like in the worst case, exponential in n time. So just from the fact that it exists doesn't mean that you'll be able to find it efficiently. Okay, so that's those are foundational things for computer science. And the positive outcome, or one of the positive outcomes out of that dream, is the idea of formal verification for math. And the most popular form is this programming environment called Lean, but there are others. And it allows you to write down proofs in a mechanized way, in a much more, basically like a computer program. So something like this. And the precise semantics is not important here, just that it's like a computer program. And this proof in English is written, so there might be an English proof of this inequality. It's translated into a Lean proof like this, and then there's a lean verifier which checks it. And if it says it checked out, you believe it. Okay, modulo some bug in the verifier. Okay, so that's very popular now. And so here's one meaning of superhuman AI mathematician that we could concretely think about. So there's a set of all math theorems, and who knows how big that set is, meaning what all it contains is we don't know most of it, and the ones that are proven by humans, and those are the ones proven by AI and verified in say lean. So we know that they are correct. And if that is bigger than this set, then you would consider it superhuman. Okay, so it's very quantifiable. And again, emphasizing AI need not be perfect, just better than humans. Okay, so having raised this idea of superhuman capability, we should now go look at how AI is trained right now to start to see like how could this arise. So just like one or two slides on this. So this is probably mostly well known to everybody here. So roughly speaking, there are these three stages of LLM training. So pre-training, where they learn to do next word prediction on a vast data set of text. And then there's mid-training, which is increasingly important, where you take the high-value data, high-quality data, and train on that for a while. It may still be just very similar to pre-training, but just high-quality data. And then there's post-training. So the first two stages give it a lot of information about the world, right? Knowing about something. And this third stage shows it how to do things, including new things. And so the simplest form is just to follow instructions. So, question answer pairs. Given this question, the right answer is this. But then there's something called reinforcement learning, which probably most people here know, which can also impart advanced skills and behaviors that were not in the training data. Okay, and so this reinforcement learning stage is the one where it acquires behaviors. Okay, so as far as we know, there's no way for AI to become a great mathematician by just, or even IMO gold level mathematician by just training on a lot of IMO examples. Okay, but I mean by just next word prediction on that. It seems like it requires to do this reinforcement learning. So reinforcement learning is the following idea. So you start with a large question bank. And now that's the AI being trained. Feed it a question, one by one. And it does many attempts, say 16 attempts, 32 attempts. And you get the model solutions. Then you identify the correct ones of those solutions and use the correct ones to reinforce good thought patterns and the incorrect ones to reduce incorrect patterns. So slap on the wrists, so to speak, for incorrect behavior. Yeah, and the terminology is, of course, very much reward punishment. Now, this human feedback, when it was started, they were actually using human answers or human ratings as feedback. So now, something to understand about reinforcement learning, which is not always appreciated, certainly by the public at large, which is still thinking about stochastic parrots and next open prediction. So in this loop, every single word or token that the AI is being trained on was generated by itself. Okay, it was given an external question. Somebody else constructed the question, but then it made many attempts, and through some process, the correct answer was maybe there's a single line or word answer, and so it can be graded easily. So the correct ones were identified, and then it's just, there's some update using gradient descent and gradient descent, which adjust the probabilities of the answers. Very simple. But the point is, every single word it's training in this process, training on in this process was generated by itself. Okay, so this is usually not emphasized enough in the popular accounts, of course. So now that brings us to the question we started with of how self-improvement happens or could happen, and also why math is well suited for it. But you'll see that the ideas may apply to many other things, and it's still an open question what all it will apply to. So firstly, we talked about, people giving thumbs up, thumbs down, but you don't need it for math because you can use lean or any other formal framework. So that thumbs up and thumbs down is not needed. You could use lean. So AI will just need to write the answers in lean, and they'll be checked by a compiler. Now, okay, lean verification is non-deterministic sometimes, but most of the time it works. Now, there's a practical hurdle right now that the lean coverage for many math fields is pretty spotty. And there's a very passionate lean community, and there's a debate ongoing about the role of AI slop, for example, because in lean, like, there's a very strong aesthetic of elegance and so on, and it's very tightly controlled what new features are added, and there's a lot of scrutiny. So extending lean is a slow process, and all these AI startups that are trying to do this don't want to wait for it. So there's a passionate debate about it. Just wanted to flag that. Okay, so that's going to be it, right? So you're gonna, if you can do it, so there's going to be lean, which will do the correct incorrect decision, and then you can train on it. So it becomes just, you need this large question bank, and then you could let it run. But how about if you even take away the large question bank? Like, that's coming from humans, right? So we are thinking to the idea of like superhuman kind of capability. How about if you get rid of the question bank and have the learner itself generate its own questions? That's what we do as humans. I mean, collectively. So how about that? Now, I tell you the reasons why this could work, right? I'm not saying this will work. I mean, it does work to some extent, as we'll see, but I don't know how far it can go. So LLMs, I mean, creativity, or you can call it bullshit, is what they're best at, right? They can just talk about anything at the drop of a hat. So sure, maybe they'll come up with wacky questions. Now, yes, it can come up with wrong questions, right questions, whatever, impossible questions. But you feed it through the give it to the same model acting as solver. So this is another thing about AI, which we humans don't have, right? There are infinitely many copies you can spin off, and they have no memory of what the others are doing. So it doesn't know that this question is coming from its own copy, right? It's just given a math question, you make it solve it, and then lean verification will read out the wrong answers. Okay, and if it doesn't generate a correct answer, fine, just don't train on it. So, and this third point seems to be the important one. You just need continuous improvement. So it's been observed that in RL, the good learning doesn't happen with very easy questions, which the model solves most of the time. It doesn't happen with very hard questions, which it really struggles with. It's the sweet spot. Let's say probability a quarter. If you do 4 attempts, it passes once. So it's just slightly hard for the learner, and those are good enough. And if you can keep that loop going, which is a big if, it continues to get better. And this was done most famously in this alpha geometry project from Google DeepMind, where they started with basically just the axioms of math, of geometry, just Euclidean geometry, and trained a model from just the axioms, and it kept generating questions for itself from the axioms and from its prior training, and then it just kept getting better, and it reached superhuman level. Like it, just because models can take in these geometric diagrams with 30 points and their relationships, which a human just can't think about. So they got superhuman. Alpha proof, and I'm just adding that that's not just at Princeton we did this too, and it worked, and I'll talk about that in a few minutes. Okay, so this does work, and as I said, for geometry, Euclidean geometry, it reached superhuman performance, and that actually is a good point there to note that one of the superpowers of these AI models is just that they're different from us, right? They can take in a geometric diagram with 50 points and make sense of it. And you and I just can't work through that. At least I don't think any human can. So that's one dimension of superhuman behavior, which they already have, right? Like they can take in 10 books worth of information in one glance. So that's a superpower. So maybe you can argue that this alpha geometry example is of that nature, like it can do geometry with 200 points, which you and I can't do. Okay. So in terms of lean, so there's the frontier model companies don't release provers that use lean, but the models that they do release, the public models that you and I work with, are actually pretty good at lean as well. But anyway, this is a plot of open lean provers, and DeepSeek is one company that does release them, and then the Princeton Gödel Prover project started in 24, and we released the two state-of-the-art models. Like our 8 billion model was better than the DeepSeek giant model for lean-based math. That was in like about a year ago, which is an eternity. And these days, you would not have a single standalone prover. You would have an agentic prover, okay, which I'm not talking about yet. So now this lean prover is all agentic, and there's a whole new wave of developments, which I'm not talking about. But let's return to AI self-improvement. And I sketched this idea that if you have a verifiable setting like math with lean, then you could see a path towards superhuman capability. But what about these non-verifiable settings? And arguably, even many domains of science, like which we think of as fairly rigorous, like theoretical physics, are not really like math. That if you pin them down, like string theory or whatever, it's not clear that they have the same axiomatic foundation. And so it's not clear that lean can be applied even to fairly rigorous fields, because they're just semi-rigorous, maybe in a certain way. All right, so we already discussed that reinforcement learning is powerful and needs a grader. And now we're saying, okay, we don't have lean, so what do we do next? So the first question to think about is a perfect grader necessary? And the surprising answer is that no. If you do these reinforcement learning loops, occasional incorrect answers don't hurt. So, because it still learns the notion of correctness. So a little bit of incorrect answers, it gets the wrong reinforcement, but it's doing this large batch training and it sort of averages out. It still basically learns the behavior. Now, don't ask me to quantify exactly how much error rate is allowed, that depends on the details. So fine. So that's a potential route to improvement. But then the next thing you worry about is, wait, okay, but you still need something, right? So some source of correct answers. And we're talking about, generating your own questions and training on them and so on. So you need a reasonably trusted source of correct, incorrect. And now we get to this point, which I alluded to at the start, right? You are trying to create something that's stronger than any human, let's say, and stronger than the existing models. So how does that work? And that's where we get to this most important idea of the talk, which is this idea of the AI actually being capable of more than we think. And it's very akin to the process of introspection. That everybody here is a researcher, so that you start thinking about a question, and then you think for days, weeks, months, years, and it matures. So this, I think, it drives self-improvement in humans. And so what is the AI analog? Now, these are very early days, but anyway, this is one analog. So this is from a press release that in August 25, and the Google team announced this model called DeepThink, and the other companies followed as well. And you can look at this press release, and maybe most of you have identified the point I'm trying to make. Considers multiple hypotheses before responding. So let me tell you what that is. Deep thinking demystified. Okay, there was a flurry of papers, like there was a Sparrow Thinker. We had a contribution to, which is the second one, which I'll talk about. There are also all kinds of other things going on. Basically, yeah, probably at this point, hundreds of papers like this. So I just talk about this one because we did this. But as I said, the ideas are happening in many papers. So remember that there are these thinking models, which we all know now, but in 2024, when they were introduced, were very novel, that the model has this thinking mode that in 2023, the models where you give it a question, it starts spitting out an answer. It was very reactive. And these thinking models have this thinking mode where they ponder the question, and they're generating these thinking tokens, which you don't even see in many of the APIs. So, and then it produces the answer that you see. Okay. So, so if there are n thinking tokens, it comes out slowly, okay, at the end. So that's why they seem to be pondering for a while, and then the answer comes. So that's the simplest form of introspection you can think of, and it was already introduced in 24. So you do get, so I had these plots showing how accuracy improves with the amount of thinking tokens or time. But for difficult problems, this improvement plateaus. Okay, so for like Math Olympiad questions, these thinking models didn't do very well in 2025. But as I already mentioned, there were these other deep think type models which did get a gold medal. And so we'll talk about this. So this kind of model is what I'll refer to as Clark Kent in the Superman myth, right? So Clark Kent. So it's okay, but it's not super good. So now there's a simpler form of introspection that you could consider, which I call sequential refine. This is a terminology from that paper I mentioned of ours. So generate a question. Sorry, given the question, generate an answer, look at that answer, reflect on it, generate another answer, etc. Now you might imagine, okay, it just produced that answer. Why should it help? But it's the same as with us, right? We think of an answer. Next morning we get up and say, wait, I missed this thing. Here's a better answer, etc. Right? So it's that kind of process. And that already is much, much better accuracy. And actually, there was this paper which showed that it could get to gold level performance at IMO, but with a lot of attempts and LLM calls. So in our paper, we introduced this open source deep think you can think of. So we call it parallel distill refine. So given a question, generate in parallel many answers, and then look at those, answers 3 or 5 or 30, and distill ideas from them. And then in the next round, you again generate many answers, etc., etc. So this is a little bit more like very much larger scale introspection. And the finding is that, if you're given a certain token budget, this is a much more effective way of producing the final answer. So I think that's all that's going on in these deep think kind of models, products that are being released. I mean, at the bottom, I mean, that's the general idea. I'm sure the details matter a lot. So this is Superman. So the base model was Clark Kent. This is Superman, because you can give it more and more and more attempts of this type, and it seems to improve dramatically. Okay, so it might use 50 calls or 500 calls, and it's reflecting on it through some pipeline like this, and it improves a lot. So implication is that the model can act as its own teacher. Why? So remember our familiar picture, right? The reinforcement learning. So this model there is like Clark Kent, right? It's given this one attempt, and that's Clark Kent. But the grader could be the orchestration of the student model, okay, which is like Superman. Its math is very accurate. So that's one way in which you can use it right away, right? You don't need any verifiable answers. This one is very accurate, and it can run this loop. Okay, so you can have just questions. You don't need any human source of answers. The Clark Kent generates many attempts. Superman grades it, and just run this. Okay, so that's a simple example of a self-improvement loop that probably will work, and it does work in the at the scales we've tried. Here's another open question: is it also a better question generator? It probably is, right? It's going to use this introspection loop to ponder the question, tinker with it, etc., and make it better. So that's potentially another way. Okay, so this power of orchestration on math, I'll tell you a little bit more about this, because we put out this paper recently. So this was the one I mentioned, sequentially just grade, solve. Repeat 100 times. Then DeepSeek released a version where they generate 64 solution attempts, repeat for 16 rounds, rank the current solutions by average score. Okay, I'm just telling you, and create a new pool of 64 solutions, each condition on, and do grading, etc., etc. Okay. All right. Stop if any solution gets full points from all 64 grading attempts. 64 times it grades. You're wondering, why are they grading 64 times? Okay, because grading is supposed to be easier than solving, right? Okay, so when we tried to do this, we discovered an interesting phenomenon, which the other papers allude to, which we call a cognitive well. So because the grader and solver are both AI, and the solver is making many attempts and the grader returns a grader report, so their reasoning gets entangled. The solver has sort of mapped out what the grader's blind spots are, right? It's some kind of a reward hacking in context, right, over many attempts. And so it's like adapting its answer to the feedback, and the grader at the end can't even tell that the proof is wrong, right? Because all the gaps it saw were patched. And the cause is this, okay? They are sharing the same inner parametric knowledge, and the solver constructed the solution over many solutions. So what's the way out? Okay, so there's something essential to realize here, and I'm kind of hinting at that. The grader is the most valuable player in this pipeline, because bullshit is easy, right? Solvers can do all kinds of things. It's the grader who has to hold the line. And that's actually a misnomer, because the model doesn't know how to solve the question. So even if the answer is wrong, it doesn't know how wrong it is, right? So that's a misnomer. The grader is just a call to the same LLM. And at best, the only reliable signal it can produce is whether it's correct or incorrect. It has no idea is the grade 5 out of 10 or 7 out of 10 or whatever, because it doesn't know how to solve the question. And the second point to realize is that the impact of grading mistakes is asymmetric. A strict grader will just force the solver to revise more and more, but get a bulletproof answer. But a lenient grader, even if it's lenient once, will say, oh, correct answer, and then game over, right? You've accepted an incorrect answer. So there's an asymmetry in grading. And so how did we get around this cognitive well? So our key idea was to rewrite proof with conjectures. And you leverage the model's helpfulness. You say, okay, look, here are these current proofs and these grader reports, and the students are struggling. Help the students by writing a new proof with the clearly stated conjectures that close the gaps. Okay, so you do that. Oh, I see. I don't have another slide with this. And then once it generates the conjectures, you now take the conjecture as self-contained math questions and ask the solvers to solve that. Okay, and that's much more reliable and much more efficient. Like the process quickly works out its own mistakes and reaches a final answer. So this is the pipeline that the conjecture extractor, when the proof is stalled, do conjecture extraction and then use and work on conjectures as new math questions. Okay, so the interesting thing, and this illustrates the cognitive well, 50% of the conjectures get disproved. So it thought that this proof that that's looking at basically should work, just this conjecture has to be proved, but the conjecture was wrong. So yeah, so I think self-questioning and doubting will be a key skill for AI, and we'll have to think about it. And I've been very interested in this metacognition idea for the last 2.5 years. Okay, so yeah, just the usual performance numbers. So they have various releases from the leading companies, and this Elatia was actually after our release. And at the time of our release, our model was state of the art of any reported performance. There's this IMO proof benchmark, and those were our models. And that over there for comparison is Clark Kent, and these are orchestrations. So these are Superhuman. And what was surprising, I believe, to the other people who do this kind of thing is the low cost of our pipeline. Because of this conjecture, it was very efficient. $31 for the state-of-the-art performance per question, and $6 for very, very decent performance. Okay, and in March, we actually tried the new model, Gemini 3.1 Pro, and actually now we're getting a scaling curve that's actually beating the Gemini DeepThink curve that was released using, I believe, the same model. So it is really a much more powerful pipeline. And so, as I was saying, this orchestrations is the way to run AI models if you're working on difficult questions. And of course, that's what the companies are doing. Okay, so are these cognitive wells hurdles for self-improvement? That's an important question as well. That AI can get into this cognitive well where it really can't distinguish truth from falsehood. Now, as I mentioned, for high school geometry, this was fine. But what about more advanced math? So the mathematicians were very interested, and these are great mathematicians who banded together and earlier this year released a challenge called First Proof. So as it says, a set of 10 math questions by these people to evaluate the capabilities of AI systems to autonomously solve problems that arise naturally in the research process. So these were basically their unpublished, unreleased work. 10 questions from 10 people or 10 groups. And so they held on to their solution and just released the question and for a week. And the frontier model companies tried to do that. And the key finding was that these orchestrated frontier models from the obvious companies claim some progress, but it seems like cognitive well is a huge problem. So if you run this, the orchestrations on these, difficult topology questions or something like that, the process converges to proofs which look quite plausible, and there are subtle mistakes, and it's very easy for the AI grader to miss those mistakes. So this is a serious issue, and I think the answers that were released all went through a human check. But if you don't have humans in the loop, it's very hard to trust the answers. This is right now a major open question. Now, of course, lean is very attractive, but as I mentioned, lean currently has not been extended to many types of math. So yeah, so often this is described inaccurately as hallucination, which is more about factual recall. And this is more subtle mistakes in like understanding the definition or something like that, or applying the definition. Okay, so now just in the last few weeks, you've been seeing that they've released proofs of major open problems, and possibly they involve humans in the loop. The frontier labs now actually have teams of mathematicians on their roles. So possibly right now there are humans involved, but probably there's genuine progress. And first proof version 2 is being launched on Friday in 2 days. We hope to submit an entry, and these are much stricter rules, and it'll be very interesting what happens. Because you can't use secret models, you have to use publicly available models, you have to release the prompts, etc., etc. Okay, so unknowns. So I sketched these self-improvement dynamics, and it's unknown if they'll somehow change or cease as we go to higher levels of math. And the interesting thing, yes, AI can generate new questions, as I mentioned, but will it find interesting new math? How would we define it? And actually, how do you define it? Interesting. And this almost certainly the answer is yes, the third one, at least in the near future, that there'll be a glut of AI-generated informal proofs with maybe very subtle bugs and not enough people to really verify them. So that's coming up. So concluding thoughts, yes, self-improvement does exist and it has been demonstrated and can arise because verification is much easier than solving. LLMs do have strong self-improvement abilities, and orchestrations is one such ability. It's actually quite freakish, what happens with orchestrations. If you should try it, with crowdcode or something, you can launch your own harness very easily, and it's quite freakish. And this quality gap with orchestration versus the base model can allow the model to, in a sense, act as its own teacher. And this raises important implications for, of course, AI safety, alignment, etc. But at the same time, you can imagine that improved capabilities through these methods could be harnessed for better alignment as well. Okay, thank you very much.
Hello. That was a good talk, but so here's my question. So, obviously it's hard in a field like this to look that far into the future, but what do you think, like in a couple years, do you think that tools like this would actually be able to, in a reasonable way, aid mathematicians at like what they're actually doing in research level math? Like, do you think it will actually be?
They're actually helping. I've talked to several, usually young mathematicians, and they are beginning to use them
And like, how do
at
you
top departments.
how would one like work collaboratively with a model like this to solve a problem?
No, that's a longer thing. Yeah, I mean, so you can see there, like people are blogging about it, not blogging, whatever they do these days, right? Putting it on social media, etc. Yeah.
Thank you. Hello, professor. Thank you for the talk. One of the strongest points you made was that departure from hard verification with lean into things that are most likely going to improve the answer, right? Where you said, hey, if it's marginally better, we can scale this up and keep going. Um, I'm curious how you think that relates to general scientific progress, because scientific progress, similar idea. You're generating hypotheses, parallel experiments, etc. If you can get some feedback, you can improve your hypothesis, etc., make some new discoveries. Do you think we have that direct path towards scientific improvement? If not, what do you think are the strongest blockers? Where does everything you said today kind of go wrong in being able to translate to like those different kinds of sciences, physics, etc.? Like,
Yeah. So um, my guess is that it will happen most in branches of science where there's fast possibility of fast iteration. So like some types of biology these days, right? The things are done at scale, right? You run whatever the samples through all kinds of machines at some pace. So you could imagine that AI would be able to make sense of the volume of data. That's one of their superpowers, and be able to suggest interesting new experiments and run that loop. So so there will be quite a few areas, maybe material science, etc. Yeah, there's a lot of data which AI could. That's one of its superpowers. Take it in and do something. Yeah. Uh, somebody, who are you pointing to?
Oh, hi.
Oh, I see. Where area?
Okay.
There. Okay.
Thanks for the great talk. I'm a physicist, so I actually have questions about how this framework can be extended over to physics. Are like
Even theoretical physics.
theoretical? Yeah. So I'm a theorist, so I have a question both for like simulations where maybe you would need, in this case, replace lean with a physics solver, but also in like pen and paper theory where you're executing derivation. From my perspective, these problems tend to be they seem a bit easier in the physics domain than they are in the hard math domain, because it's easier to arrive at an answer in a lot of the problems that we work in. But I'm curious how you've thought about that extension.
Yeah, no, I'm not enough of a physicist, just undergrad level. So, uh, yeah, I would love to hear your ideas. We can talk in the break.
Yeah, absolutely.
So yeah, I think that I just laid out what is available in AI and probably how it'll go. Yeah.
I have a question. So when you talk about solving using lean, right, you can in some sense get a binary value, so whether something is correct or incorrect, right? In a very long proof, but lean would give you a binary answer, but it doesn't necessarily give you a more fine-grained answer as to where did something go wrong, right? Does it?
Oh no, it does. It's a compiler, so it may not be the logical error, but like it'll tell you where it is seeing an error.
It is saying another. Okay, so would it be possible to actually use lean traces to figure out where an answer went wrong and actually use that to improve an answer?
Yeah, that's done. Yeah, also in our Gödel prover. Yeah.
Okay, got it.
Yeah.
Thank you.